talk about motor installation of motor blocks. And a motor block is a term that is, if you're going to install 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 motors, and you're going to supply them from one main circuit breaker and divide up the load at a auxiliary gutter or something like that, and go to a bunch of disconnects and go out to a bunch of motors, that's a motor block. So we're going to be talking about motor block a great deal. There's a lot of kinds of motors. As you know, we've studied the different family types of motors: AC, DC, squirrel cage motors in AC, induction motors, and so on. There are single-phase motors, three-phase motors. And if you're hooking any of these up, we first start out with finding the full load ampacity of the motor. That means under full load, what can it supply? And it's horsepower rated. A horsepower rated, and then it's voltage rated after that, and then we find the full load current from that. So let's look at a single phase motor first, and let's pick out, we need, for instance, a 2 horsepower motor, and we're going to, no, let's go down to 1 horsepower, because a 2 horsepower we generally wouldn't use in a single phase circuit with 110 volt supply. We would be required by code, well, that's a whole different Oprah, but we would be required by code to go to 240 at least. And but let's say, oh, let's do that. Let's pick out a 2 horsepower motor, and we're going to say we're going to go at 230 volts. What would my full load ampacity be? We're going to come down here to the 2, and we can see that we would be pulling 12 amps full load ampacity. Now, assuming that we have a motor at 2 horsepower at 230 volts, single phase, it's going to draw 12 amps at full load. Now, we're never going to assume that a motor is not continuous duty unless we know for sure it only runs for a little while at certain times and so on and so on. Unless we know for sure that it's not continuous duty, we assume that it is continuous duty. So what we do with a continuous duty motor, we take its full load ampacity, and when we want to find the wire size, we're going to take that ampacity and multiply it times 125%. That means that the wires will never be loaded over 80% of its full load ampacity of the wire. So we're going to take the ampacity of the load and multiply that times 125%. So in the case of 12 amps, that would be 1/4 of 12. It's 3, right? And so it'd be 15 amps, right? Okay, so that's the ampacity. We would pick a wire for this thing, and we call that wire coming to the motor from the motor starter or from the safety switch down to the motor starter. We call that the motor branch circuit. So let's start talking about motor branch circuits from now on. And we're usually going to assume that they draw 125% because they're continuous duty. So we'll almost always multiply the full load current by 125%. Now let's look at a 3-phase motor. 2-phase motors you'll see so seldom that it's not really worth talking about. Let's go down to a 3-phase motor. The most common motor you will see is a 3-phase squirrel cage motor. And a 3-phase squirrel cage motor is very efficient. It lives for a long time. It does its job. It's a great motor, and because of that, they're the most common motor in the whole world. So let's go back to our 2 horsepower motor, and we're going to go 230 volts 3-phase, and we now can see that would be a mere 6.8 amps just because it's 3-phase. It's still operating at 230 volts, but we have 3 energized conductors, and it's balancing the load between those 3 conductors. So we're going to draw 6.8 amps. In single phase, it was 12 amps to do the same work, right? Because the horsepower rating is the amount of work we're actually going to do, right? Okay, so we're only using 6.8 amps. Can we see now why 3-phase is preferable? It's only costing you 6.8 amps to do 2 horsepower worth of work. Whereas with a single phase, it costs you 12 amps. And you pay for VAs. Voltage times current is what you pay Edison for, or whoever you happen to have serving you electricity. So now, if we had 6.8 amps and we wanted to select a conductor, we would multiply that times 125% again. So now we have the ampacity of the wire, right? That we have a minimum ampacity. So let's start out with doing that. Now, I want to just very quickly talk about locked rotor current. Locked rotor current is the inrush that happens before the magnetic field builds up in a motor. And that inrush current can go on for a second or two, and the starting equipment has got to withstand that instantaneous rush. So we could find that in 430-250 full load current, three-phase alternating current motors. I'm sorry, that's the wrong one. That's three-phase motors. But I believe it's a page past that we could find our locked rotor current. And the only thing we really care about that is that it's that's the amount of inrush we're basically going to have. Okay, so now let's select a wire. Let's go back to our no, let's start a whole new motor block. So let me hit pause for a second and draw on the board just a little bit. All right, so let's say we have this motor block, and we're going to assume a couple things, that we have three-phase 230 volt power supply, and it's coming from a distribution panel someplace else, and it's coming to an auxiliary gutter, and we're dividing it up. And we've talked about tap rule conductors before, right? We've talked about tap rules, right? Okay. We're going to talk about that again today. Now, we're going to assume that we have a 2 horsepower motor, a 7.5 horsepower motor, a 15 horsepower motor, and a 50 horsepower motor. Now, we have a fuse disconnect for each one, and we have dual element time delay fuses in each one of those. I'm going to figure out what that means later. But now, we first need to take our full load ampacity and find our minimum branch circuit conductor, motor branch circuit conductor. We need to find our minimum branch circuit conductor ampacity. So let's look at our first motor. It's only draws 6.8 amps. What's 125% of 6.8? Say again? 3.5. I don't think. Oh, 8.5. Thank you. So we're going to say that's the minimum motor branch circuit ampacity. And we're going to have a quiz sometime soon where you will be required to find the minimum branch circuit ampacity. That may not have anything to do with the wire size, right? Because what wire will we use? Now, I'm going to tell you something that I don't want you to misinterpret and interpret it to other things. Motor branch conductors, motor branch circuit conductors may be no smaller than number 14. Now, there are other times when you can use a smaller wire, but to feed a motor, you can't use anything smaller than a 14. Now, this is below 100 amps. Our equipment is anyway. Most of it is, right? All of it is below 100 amps. And we're going to assume that we have no terminal markings or no equipment temperature markings on our equipment. So that means we have to use 60-degree temperature rated ampacities. Even though we're using higher ampacity wire, we're using 75-degree wire, we're using XHHW is what we're going to use for all our wires. XHHW is a 75-degree rated wire. So in our first motor, our number 14 is good for up to 20 amps, right? And that's more than enough. So our wire is number 14, which is good for 20 amps. And whenever you do one of these motor blocks, I want you to put the ampacity that the wire is valued at that temperature rating next to the size of the wire. So in this case, we have a number 14 that is good for 20 amps, and our motor load is only 6.8, and the maximum, or I should say the minimum wire ampacity is only 8.5. Well, 20 is way more than 8.5, right? Okay, let's go to our next motor and do the motor branch circuit conductors for that. We have a 7.5 horsepower motor, and it draws how many amps? 22 amps. So what is 125% of 22 amps? Say again? 27.5. And that's the minimum motor branch. Now it's not going to write. What's going on here? Motor branch circuit conductor, and that's 27.5. Now, where are we finding our ampacities? We're going to 310.16, right? Let's go to 310.16, and we're going to look down the chart. We need something that's more than 27.5 in our far left column. Number 10 will be just fine, right? Now, we're going to use number 10 wire. And in this case, what ampacity is number 10 good for? 30 amps. Very good. All right, so we're going to use, for our motor branch circuit, 30 amp wire, because that's more than 125% of our full load ampacity, right? That's more than enough. Let's move down to our third one. And our FLA is 42 amps, and 125% of 42 amps is what? 52? Okay. So our minimum motor branch circuit ampacity is 52.5. But is that the wire size? No. The actual wire we're going to use is going to have to be a number 6, which is good for 55 amps. Okay, now 125% of 130 is 162.5 amps. And I want to tell you one more thing about this whole thing before we go too much farther, but let's find our ampacity for our wire. Our minimum ampacity is 162.5 amps, and so we can use a 3/0. And what ampacity is that good for? Well, that's so good. 155? Oh, 165. 3/0 is good for 165 amps, which is just enough, right? All right. Now, I want to tell you something ahead of time, just tell you something, that when if we have to calculate our feeder that's coming to our equipment, and often we will, the minimum size that we can make that wire is 125% of the biggest load, which in this case, our biggest load is our 50 horsepower motor that draws 130, and 125% of that is 162 amps. And then we're going to add the rest of the full load ampacity, so 162.5 plus 42 plus 22 plus 6.8 is how many amps? 200 and what? 233.3? Is that right? 251 amps. Okay, well, one of the two. But we know that 250 kc mil is going to allow 255 amps to flow, right? Okay. Now, I don't want to get into that right now, but let's just say, is there such a breaker as a 255 amp breaker? I don't know. Yeah, well, can we do that? I think we'd have to go down in this case, but let's come back to that. Let's say that it's a 250 amp circuit breaker. So it's a 250 amp circuit breaker. And you'll see why that's important in a minute. Okay, so we've figured out our ampacity of our motor branch circuit, right? And that would be the same for these wires up here. That's still motor branch circuit, right? Then, another thing we might want to find out is what motor starters we have to have. Now, if you looked in your book, back on page 389, you'd see the NEMA selection chart for the starters. Now, the reason you need to select the size of the starters is because at some point we're going to start selecting the overload heaters, and they're sized to the starter, the size of the starter. So we would then, our next step might be to size the starters. Okay? Now let's assume we've done that already, but we're not going to do that right now. Let's go up and look at our fuses. Now, what ampacity, how do we select the size of our fuses? Hang on one second. Let me see what... Uh-oh. Oh, I hope that didn't all disappear. I think I hit the wrong button. I think I should have hit the little camera button instead. Okay. Let me hit pause a second, see if I can get that back. Okay, we're at 430.52 for a reason. We're going to select motor branch circuit protection. That's the fuses or circuit breakers that protect the motor branch circuit. These are not for overload. The overloads and the heaters are for overload. This is motor branch circuit protection. If you use any other phrase, I'm not going to be happy. I want you to use that phrase, motor branch circuit protection. All right? And look at these things on the left. That's the type of the motor. Okay? What kind of motors are we using? We're using AC polyphase motors. Okay? And we're using dual, look at the top, and we're using dual element time delay fuses. Look right up here. This is the one we're using. And since we're using these kind of motors, we're going to be selecting 175%. And you're wondering, what the heck does that have to do with anything? That means it's 175% of the full load ampacity of the motor is the fuse size. Now we're going to find that fuses don't come the exact sizes we want. All right, now looking at the motors, we now know, or the last chart we looked at, we know we're going to take the FLA and multiply that times 175%, or 1.75, and we're going to get our fuse sizes. Now, they won't always agree with the possible fuse. So let's take our first motor, and we had a 6.8 ampacity, and that times 1.75 is what? Okay, now what we need to do is we need to look at our standard ampere ratings. And these are the common fuses and circuit breakers we can find. Now, I want to take a couple of notes about this. I want you to notice that in this section right here, all the way down to here, is fuses and circuit breakers. But down here, we have just a couple that are fuses only. So 1, 3, 6, 10, and 601, you need to remember those numbers. 1, 3, 6, 10, and 601 are fuses only, and for motor control, 1, 3, 6, and 10 are very handy for small motors, but they're fuses only. Okay? All these other ones are fuses or circuit breakers. So let's look at our first motor, and here we have a place where we have a 6.8 full load ampacity, and our ampacity for the fuse maximum should be 11.9. Now, the code says that if the motor does not start with that, you may go to the next higher fuse. So in other words, it's just saying we can go to the next higher fuse if we need be. So is there a 12 amp fuse? No. Is there 15 amp fuse? So we would use a 15 amp fuse in our first motor starter. Okay. Now, let's go to our second motor, and it's a 22 amp motor, full load ampacity, and 175% of that is 38.5. Do you see a 38.5 circuit breaker or fuse? No, but we have a 40 amp, and yes, we can go up to the 40 amp. So we would go up to 40 amps in the next one. In the third motor, it draws 42 amps, and our 175% of 42 amps is 73.5 amps. What's the nearest fuse to that? 80 amps. I would have sworn there was a 75 amp fuse, but there isn't. Okay, so we've got to go up to an 80 amp fuse. And then on our last one, 130 amp full load ampacity may require up to a 227.5 amp fuse. 225 should be big enough. No, it's only 2.5 more, but it might not start. So we're going to go up to 250 amps. Now, these are dual element time delay fuses that we've just selected. Then we would have to select motor starter, no, I'm sorry, not motor starter, safety switches, disconnects, EXOs, fuse disconnects, in other words. What size would we pick them out in? Well, they only come in a few sizes. And I'm going to give you a handout that has all the different sizes. So we're not going to do that right now. So let's go back to our drawing. Finally. All right, so we picked out a couple fuses here, and we picked out a 15 amp fuse for this one, and we picked out a 40 amp fuse for this one. Is that correct? And for the next one, we picked out an 80. Is that correct? Okay, and then for the last one, we picked out a 250. Is that right? Is it 250? Okay. So now we have almost everything selected as far as sizes. We haven't selected the size of the disconnects. We haven't selected the sizes of the starters or the starter overload heaters. But we'll do that in our next little adventure. But now let's look at our tap conductors. We said that we had, that one's wrong. We said we had 12 feet, 9 feet, 12 feet, and 9 feet. Now, what that has to do with is we have a 250 amp circuit breaker up here, right? That's our main overload protection, right? I mean, not overload, but our main overcurrent protection device, OCPD. Overcurrent protection device is 250 amps. Now, you remember we talked about tap conductors last week or the week before, right? Now, in the 10-foot tap rule, it's only 10%, right? That's the tap rule minimum. Now we're going to see the application of that minimum and the load overriding it sometimes again. So we're going to go over that again. And let's look at our 10, where we have two places where our 10-foot tap rule can apply. And at 250 amps, what is 10%? 25 amps, right? So we've got a 25 amp minimum conductor size. Well, a 25 amp minimum conductor size means we could use a number 12 in our, or could we? That's 25 amps, right? But our load in our motor here is being supplied by a number 10 wire. So we don't want to go down to a number 12 for the tap conductor. So we're going to have a number 10, which is good for 30 amps up here. because our load is bigger than our tap rule minimum, right? Now let's go to the last motor, which is a 10-foot tap rule also. 10-foot tap rule minimum says we have to have at least 25 amp wire going from this point down to this point, right? That's our tap conductor. But our load is like 160, it's 130 amps, and our conductor we're using to do that is 3/0. So we're going to have 3/0 up here, which is good for 165 amps. Okay, now our 10-foot tap rule doesn't apply if it's a hair past 10 feet. And that means the conductor, not the conduit. So if you've got a 10-foot conduit, if you've got a 10-foot conduit, you're no longer under the 10-foot tap rule. Your conductors are longer than 10 feet long. So 12 feet, we're definitely under our 25-foot tap rule, which means we have to take a third of the full load ampacity of the overcurrent protection device that's supplying this set, which is 250. What's 1/3 of 250? Is that right? 82.5 amps. Pretty close. 82.5 amps. So what size wire will carry 82.5 amps? Let's go back to our 310/16. And we would have to have a number 3, which is good for 85 amps. Number 3 for 85 amps is not nearly enough for this last motor, right? We have to have our 3/0 at 165 amps. But let's go back to the first motor. We've got a number 14, right? Can we put number 14 wire up here? We cannot, because the tap rule minimum says that we've got to have 1/3, which is 82 amps or thereabouts. So we're going to have to use a number 3. And how many amps is number 3 good for? Now look at this. We've got down to this disconnect, we have this great big number 3 wire that supplies, was good for almost 100 amps. But down here below the disconnect, it's all number 14. It's only 20 amp because it's only a 6.8 amp load. Why does this wire have to be so big? Because a tap rule minimum conductor. We're protecting, we're making sure that this is going to run nice and cool, so it's not going to be the source of heat to burst into flames. Okay, and that's what this tap rule minimum is all about. Okay, so we figured out a lot of stuff today, right? Okay, what have we left out? Have I left out anything? Third motor? Oh yeah, our third motor draws 73.5. I mean, it has an 80 amp fuse and a 55 amp, and it's a number 3 minimum also, isn't it? Yes. Okay, so this is number 3 minimum, which is bigger than number 6, right? So our minimum, again, is bigger than our load. So we can use the tap rule minimum. But if the load is bigger, like on this last motor, the 50 horsepower motor, the load is much bigger than the tap rule minimum. Okay, so we're going to go with the motor load conductors. Okay. All right, just to make sure that we've done as much as we can today, let's pick out our motor starter sizes. First of all, this is how many horsepower? It's a 2 horsepower. So looking at page 389, we would look down our horsepower, which is, first we have to decide on single phase or polyphase. We're in polyphase, right? We're using 3-phase motors. So we're going to go down to a 2 horsepower. And at 230 volts, we cannot use a double lot size because that only goes up to, and 230 only goes up to 1.5 horsepower. So let's go down to a size 0 at 230 volts up to a 3 horsepower. We're only using a 2 horsepower, so we could use a size 1/0. we call that 1/0. Okay, now let's go over to the next one, and it's a 7.5 horsepower at 230 volts, 3-phase. One comes out exactly on it, a number 1. This is a number 1 size. Okay, let's go to our next one, which is 15 horsepower at 230 volts. We come out exactly on a starter again at size 2. So we have a number 2 starter. And on the last one, we have a 50 horsepower. And at 230, a number 3 is too small. Notice that only goes up to 30 horsepower. And at 230 volts, our 50 horsepower is exactly on a number 4. So a number 4 starter for here. I'm looking at page 389. Okay. And we're going to stop for today. We're going to pick out motor overloads another day. But that's a whole other step. But we're almost there. We now can pick out the conductors for the whole thing, right? So the next thing we would need to do is be able to pick out the size. We've picked out the size of the starters. We need to pick out the size of the overload heaters, the size of the conduits, the size of the auxiliary gutter, and if the conduit and wire has not been run back to the distribution panel, we might have to be able to size the feeder circuit, and that's not a big deal. Okay, so that's it for today. I hope you enjoyed that.